Okay, the purpose of this video is to do a worked example of the Laplacian as it's applied to a scalar field. So I wanted to very briefly discuss what a scalar field is. All of you know what it is. Maybe you just haven't heard it called that, but a scalar field is just a field where a scalar value is assigned to every point in space. And obviously within the domain that we're talking about. So a real common scalar field used in fluid dynamics is a pressure field. And also, temperature is also a very common one as well. So temperature, pressure, I'll put those here, temperature, pressure, fields, all very common examples in engineering of a scalar field. Okay, so let's just run through this worked example. And what I wanted to make sure of is just so you could see me work through a problem and see all of the steps that I choose not to skip. And really just to help you with understanding and being comfortable with the notation. So, all right, so what we're after is we want to figure out the Laplacian del squared of f. So the upside down triangle, just as an aside, the upside down triangle is referred to as a del, which is confusing in a few ways because so is this partial derivative symbol is also referred to as del. The other thing that people will refer to it as is a nabla. And if you double click on any of the equations that I've created in this MATLAB live scripts, you'll notice that the LaTeX code, the LaTeX command for the upside down triangle is actually nabla. So there you have it. So let's find the Laplacian of this scalar field. Okay, so what we're really after is we want the second partial derivative of f with respect to x plus the second partial derivative of f with respect to y plus the second partial derivative of f with respect to z. Okay, so let's just go ahead and plug these things in. Del xx of xy squared plus z cubed plus the second partial derivative with respect to y of xy squared plus z cubed plus del z of my vector, or of my scalar field, xy squared plus z cubed. Okay. So what we want to do, the way that I try and think of this as just applying the applicable first partial derivatives. So let me write this down. So apply, do it in a different color. Let's apply the first partial derivatives. Okay, so what this will look like is notationally, I just want to show you what this looks like notationally. I think you could do it in your head. But del x, and then what I'm going to do is break it out and write a del x again. Okay, and this just helps me keep track of it. Plus z cubed. And I'm going to do the same thing with the y. And we'll do the same thing with respect to z. Okay. And now let's go ahead and take the derivatives. So in the first term here, we still have that del x on the outside. And the partial derivative of xy squared plus z cubed with respect to x is just y squared. Plus del y, so we have the del y on the outside. And here we just get 2xy, the first partial derivative of our field f with respect to y is just 2xy plus del z. And what we have here is we have 3z squared. Okay. And now the next step is just to apply the second derivative, really. But according to our notation, we're just going to take the derivative again, right? So apply partial derivatives again, right? And I will put the second partial derivative because that is what it is. That is what we're doing. But notationally, you can see that we're just taking the first derivative again, okay? All right, so the next step is just doing that, and what you end up with is the first term, you get 0. Second term, we get 2x, and the third term, we get 6z. Oh, sorry. I was right, 2x. And then, huzzah, 2x plus 6z is the solution, okay? And if you read the statement above, so a Laplacian applied to a scalar field, if you end up with a vector, you've done something wrong because a Laplacian applied to a scalar field is always going to give you a scalar, and that is exactly what we have. So just to complete this, del squared f, and there we go.